what's another operation we could do with linear vector functions? So if we have this system of linear equations, then the left-hand side of it, remember we can treat this as a linear vector function whose matrix is just all of the a's, like this. Okay, so what are other operations we could do with this linear vector function? Well, since this linear vector function produces a vector as its output, right, the two vector operations are vector addition, which we've talked about, and scalar multiplication, right? We could take this vector function, this linear vector function, multiply it by a scalar, which I'll call k, and this would produce k a11 x1 up through k a1n xn, and so on. Right? So what's that going to do to the corresponding matrix? Well, if you just look at all of the coefficients in this linear vector function, all the coefficients have just been multiplied by k. So if we multiply a matrix by a scalar, the result is just multiplying each entry by that scalar. So k a11 up through k a1n down to k am1 up through k amn. Or if we wanted to be a little more concise about this, we could have written k aij like this. Of course, if I asked you just to guess what a good definition for multiplying a matrix by a scalar would be, this is probably the definition you would guess. So everything is making sense here, but just conceptually, it is important to realize that this definition for multiplication by a scalar is not arbitrary. It actually comes from this operation on linear vector functions. All right, so this is scalar multiplication for a matrix. Let's actually do one. What is the scalar product of 4 and this matrix? So 4 times the matrix 2, 7, 0, minus 5. Oh, a note on notation. For scalar multiplication, we just write the scalar next to the matrix. So there's no operation, no symbol that we put in between the two. You just juxtapose them or put them next to each other. All right, so what is this? What is this? Well, just multiply entry-wise. So 4 times 2 is 8. 4 times 7 is 28. 4 times 0 is 0. And 4 times negative 5 is negative 20. Okay, so just like with vector addition, just like with matrix addition, scalar multiplication is, when it comes to computing it, scalar multiplication is pretty humdrum. There's not too much going on. Okay, but now we have an addition operation and a multiplication operation, scalar multiplication. So when we have both an addition and a multiplication, it's possible to write down expressions where both of those operations show up. So things like, k times matrix A plus matrix B, plus a matrix C afterwards. I guess a convention, lowercase will always be a scalar, uppercase will always be a matrix. So in this sort of expression, we have some scalar multiplication happening and we have some matrix addition happening. And so to work with this sort of expression, we need to know, well, how is it that the multiplication operation interacts with the addition operation? In other words, we need to know some laws of algebra. In all of our other systems where we have a multiplication and an addition, the multiplication and addition interact in some nice ways, things like distribution. And it turns out, of course, since addition and scalar multiplication for matrices happen entry-wise, all of the nice things that usually happen with addition and multiplication also happen for matrix addition and matrix scalar multiplication. So if you have a scalar multiple and a sum of matrices like this, you might expect that you could just distribute like this. So scalar k times matrix A plus scalar k times matrix B. And this is true. If you just write out everything in terms of entries and do all the operations entry-wise, the entries for both sides of this equals are k times aij plus k times bij. So scalar multiplication distributes over matrix addition, as you would expect. There's actually a different version of distribution, which is the addition could be on the scalar side instead of on the matrix side. So that would look like maybe r plus s. So again, I'm using lowercase to indicate that these are scalars. Scalar multiplication with a matrix A. So you might guess that, hey, is this the same thing as little r times A plus little s times A? And if you write everything out in terms of matrix entries, both sides of this equals are r times little aij plus s times little aij. So this question mark is not a question mark anymore. It's actually verified that these are true. So scalar multiplication distributes both ways. It distributes over matrix addition, but also over scalar addition. Another property that we should check is associativity of scalar multiplication. So this is if you have two scalars, say r and s, and you have a matrix that you're multiplying by s, and then afterwards you multiply by r. Well, what if you did the scalar multiplication first and then multiplied by the matrix? Are those the same thing? Well, if you write out everything in terms of entries, you get r, s times aij for both of these. So yes, these are equal. And then finally, multiplication by your scalar 1 and your scalar minus 1 has some nice properties. So for matrices, or for 1, I mean, if you do scalar multiplication by 1, you might hope that you just get the same matrix back. And indeed that's true, because here we're doing 1 times aij, but that's just aij. What makes minus 1 special is a little bit less obvious. What makes minus 1 special is you might hope that scalar multiplication by minus 1 gives you the additive inverse of a matrix. Right, so here I'm writing this minus sign to denote the additive inverse. And it's not it's not 100% obvious that multiplying by minus 1 does give you an additive inverse, if you just think about sort of scalar multiplication, not component-wise, but just conceptually. This isn't totally obvious. But if you look at these things entry-wise, then it is totally obvious that multiplying by minus 1 just gives you the additive inverse, because this is minus 1 times the matrix of entries aij. But if you do this scalar multiplication, that's negative. That's a matrix whose entries are minus aij. But we've noted before that this is exactly the additive inverse of the matrix A. So multiplying by 1 and minus 1 both do what you would expect they do.